of the Spitzer Space Telescope. Just briefly, the Spitzer Space Telescope was launched in 2003. It was an infrared observatory, and it lasted until just last year and finished its mission in January of 2020. So, but I'm going to start a little bit earlier than that. One of the things that I was told once is don't underestimate the power of telling people what they may already know. So I'm not quite sure how many people know as much about infrared astronomy, although I know there's a few people who may be outside of the regular physics colloquium who are attending, but I'll do a little bit of history of infrared light and infrared astronomy. And that really starts with Sir Frederick William Herschel. He was a German, but he had emigrated to England and had become supported by the King of England, King George, the same King George that we kicked out of the 13 colonies when we became the United States. He and his sister Caroline used to build telescopes. He was a royal astronomer, and so they did a lot of catalogs. But the thing that he's most famous for is that in 1781, he became the first person to actually discover another planet. All the other planets were known to the ancients, but it was using telescopes that he discovered Uranus. He didn't want to call it Uranus. He wanted to name it after his patron, George's star. Nobody else was going to call it that, so then they went with Uranus. But really, I think what he should be known for a lot more is that in 1800, he decided to do an experiment. He was trying to figure out whether the different colors of the rainbow had different temperatures. And so he built, several thermometers. He had a prism. He separated out the light and was putting one of the thermometers within different colors while the other ones were outside of that. But what was interesting is once he pulled the thermometer away, what he thought was outside of the light, the thermometer still got warmer. And so from that, he deduced that there was light falling on that thermometer, even though his eye wasn't seeing what that light was. It was later dubbed infrared, but when he originally published it, and this is an image of that paper, it says experiments on the refrangibility, which is just refraction of the invisible rays of the sun. Think about that. Use the invisible rays of the sun. It's just sounds ridiculous, but he had done his experiment and he could show that, and others could reproduce it, that there was light, had energy, was falling on the thermometer. The thermometer absorbed that energy, changed its temperature, just like it did when it was in sunlight. So this was the first inkling that light wasn't just what our eyes could see. So why would we want to do astronomy in the infrared, since I'm not just going to talk about infrared light? The important part is when we're talking about wavelengths of light, in fact, the universe emits in all wavelengths, lots of different wavelengths. So it's critical to do it in all those wavelengths. But infrared in particular has an advantage in that, in this image, and with one of my colleagues who's demonstrating this, Dr. Luisa Rabul, is you can see through certain things which optical light can't penetrate. So that way, particularly dust in the universe is very easily penetrated by infrared light. Now notice that that's not, infrared is not the only way to look at things, because if you look at her glasses, notice we can't see her eyes in the infrared, while we can see those, of course, in optical light, or else glasses wouldn't work. And that's really why we build greenhouses out of glass, is because when optical light falls in, warms the interior starts emitting infrared light, but the glass traps it in. This is very much the effect that you have with your hot car in the summer. So there are things that will block infrared light that don't block optical light, but in particular, there's a lot of things that infrared light can penetrate. Also, anything that's warm at whatever temperature emits light, but things that are hotter emit more optical light and ultraviolet light if they're even hotter, and so on. But things that are cooler or warm emit infrared light. And in this case, if you look at the dog, you can get a sense of its fur coat and sort of where it's standing, but you're not getting a sense of its temperature. But if you look at it in infrared light, you're getting a sense that the fur coat is doing exactly what it's meant to do. There's not much infrared radiation. There's not much heat escaping by radiation from its body, except it is losing heat through its ears, its eyes, and of course, when dogs pant, through its mouth. And of course, this is a healthy dog, so it has a cold nose. You can see there's a lot less infrared light coming from it. But, sort of taking that into account, then you can see why infrared light is so valuable to observing things, particularly things that are warm but not super hot to the point of glowing in the optical. So on the left, we have a sink, and I can ask you, is the water hot or cold? Looking at that image, you don't have enough information to answer that question. But if you were looking at an infrared image, you can easily answer that question. That is, if the water is emitting a lot less than its surrounding, it's most likely cold water. But if it's emitting a lot more than its surrounding, then it's warm water. But here, also notice that now which of the faucets is the cold water faucet versus the warm water faucet. Notice that as the water is flowing here, it's cooling things down, so it's darker under the right faucet. But now it's not glowing under the right faucet, but there's a glow under the left faucet. So you're getting information which is not easily obtainable again in a single image. Same thing here. Is the hair dryer on or off? Well, the picture doesn't let you really see whether the button for on or off has been pressed, but if you had an infrared image, you'd see if the hair dryer was working. Again, more information because infrared carries extra information here. So, of course, from Herschel until the 1960s, there was no real development in infrared astronomy for sort of two particular reasons. One is transmission. Our atmosphere is not very favorable in transmitting infrared light. Notice that here, this is more transmission, that is more light getting through. So you have these little, what we called windows that infrared light can pass through, but a lot of it is flat, which means a lot of infrared light is not getting through at all, mostly because of water vapor in the atmosphere, because that's that's the key molecule that traps a lot of infrared light in our atmosphere. Of course, you've heard about carbon dioxide, being a greenhouse gas and greenhouse warming. First of all, the water vapor is the most important greenhouse gas because it blankets things the most. The sinister thing about carbon dioxide is that its absorption is in particular in these narrow bands where water doesn't absorb. So suddenly these windows where emission was going away from the Earth and taking heat away from the Earth is being closed off by carbon dioxide. So it's a very bad combination when we have both of these, but certainly not great for astronomy either, because you need light to fall onto the ground. And in the infrared, you get these narrow bands in which you can look at from the ground, but many wavelengths, as you can see, beyond 20 microns is very hard. There's no transmission of the atmosphere. But to make things even more complicated is that the atmosphere itself is warm and therefore emits infrared light. And so you're looking through something glowing, trying to see faint objects beyond it. So those are two reasons, generally speaking, why infrared has not been done, or it was done in a very limited fashion from the ground. So what we're used to when we're looking up at the night sky is that if you look at in the visible, sky is blue. In the infrared, again, the sky is warm, it glows. At night, of course, there's no scattering. The blue color of the sky is because it scatters sunlight. But in the infrared, the temperature difference between day and night isn't that much, and therefore the sky is still glowing. So it makes it very difficult to do astronomy from the ground. So that's the thing. So you want to go into space so that you don't have the atmosphere, both because it's not absorbing anymore and also it doesn't glow in and of itself. And so why would we want, again, to do astronomy? What is it that we'll see in the infrared that we may not be seeing in the optical? So here's a fairly famous constellation, the Orion Constellation. If you have not seen those blue lines connecting all those stars, you either haven't been squinting enough or haven't been drinking enough. But that's meant to be Orion the Hunter, and those are stars mostly. And what you're seeing is stars are very hot, their surface is very hot. And as you're familiar with your electric stove or burning a burning match or any burning wood or somebody doing some sort of welding, something that's very hot, it will be emitting a lot of light. So you can tell that, that's what stars are. They're hot there. But what happens when we look at it in infrared? Infrared is very different. It is, you can see here, sorry for the, somehow it's changed size, but anyway, the all of this stuff, this gas and dust that's surrounding all of these regions is glowing. It is emitting light. It's not being fueled by fusion, but it's being warmed by the stars and by various other activities, by various other processes. And so they are warm, but not as hot as the stars. So they're not emitting optical light, but they're warm enough to be emitting infrared light. So a great deal of the universe is warm, but not hot, which means a great deal of the universe is emitting an infrared light, but not optical light. And so this makes things very useful in terms of studying various different things. From one is the cold universe, things that are colder than that emit principally in the optical. The dusty universe, dust often absorbs the hotter emission from stars or other processes and then re-emits it in the infrared. There's the chemical universe. There's a lot of chemical things that have signatures in the infrared, so we can pursue different, particularly complex molecules in the infrared. And the other aspect is that the universe is expanding. As the universe expands, the expansion is stretching out the wavelengths of light. So things that had emitted in the UV and the optical, by the time they reach us because of the expansion of the universe, they are now in the infrared. So the far distant universe is also primarily in the infrared. If we just want to simplify things, this is a very quick way of doing it. That is, stars generally anywhere, 10,000 degrees-ish. Our sun is around 5,800 degrees Kelvin. This is what's called the black body spectrum. That is, this is the characteristic way that they emit. The shorter wavelengths drop off quickly, but sort of this is visible in ultraviolet. And then if it gets cooler for 1,000 degree stuff, the stuff near stars, you get near infrared, that's 1 to 5 microns. But then if you get much cooler into hundreds of degrees Kelvin, that's the far infrared, which is the stuff in interstellar space. So in the 80s, there was this, actually starting in the 70s, they decided to do that NASA would do what were called the Great Observatories project. And the Great Observatories would be telescopes that would be put above the atmosphere to take advantage of space, which in the case of the Fermi Gamma Ray Observatory and the Chandra X-ray Observatory, those are wavelengths that fortunately do not penetrate our atmosphere at all. Then there's the famous Hubble Space Telescope, which looked in the UV and the optical and a little bit in the near infrared. And that was not because optical light doesn't penetrate the atmosphere, but certainly there's the waviness and cloudiness of the atmosphere doesn't get in its way. And the fourth and last of the great observatories was the Spitzer Space Telescope. One of the reasons was that they needed to develop the technology for it, because that needed the greatest technology development. So it was a consortium of multiple different organizations, including JPL, Caltech, Cornell, the Smithsonian Astrophysical Observatory at Harvard, University of Arizona, Ball Aerospace, and Lockheed Martin. And to keep the telescope cool, we used several novel techniques. One was, again, obviously the telescope isn't that many times the size of the Earth, but certainly what we did was a novel orbit, which is we kicked it away from the Earth. This is called an Earth trailing orbit, so that when the Earth is absorbing the heat from the sun and re-radiating it, it does not fall on the telescope. We have a sun shield, so the sun is permanently blocked from falling onto the telescope. But we also flew with a lot of liquid helium, and the liquid helium would boil off and cool off the telescope tube so that we could actually go down to about 5 degrees Kelvin, although we didn't need to operate at 5 degrees Kelvin all the time. But that's as cold, we could get as cold as that. And we sometimes needed to look at the longer wavelength infrared light so that the glow from the telescope itself would not be interfering with our observations. So the telescope was launched in August of 2003. What's called the Cryogenic Mission lasted until 2009, or the original requirement was that we would last 2.5 years with our liquid helium. We actually lasted more than 5.5 years, which was a great testament to the engineering. And then we've done what's called the warm mission, which is because we didn't have liquid helium to keep the telescope cold, we warmed all the way up from 5 degrees Kelvin to 30 degrees Kelvin. Hardly warm by anybody's standard, but certainly warmer than many of the instruments that we were running could stand. But we could still, a couple of our instruments still functioned. And then we lasted until January 30th of last year. The telescope itself was named after Lyman Spitzer, who in 1946, 11 years before the first satellite, which was Sputnik, and 12 years before the formation of NASA, he wrote a scientific paper on the astronomical advantages of an extraterrestrial observatory. Think about this. This is long before anybody has any sense of actually being able to go into space. And he's suggesting that we should be putting telescopes in space. And he's the founder of the study of the interstellar medium, which is the dust and gas that form stars from between stars. And of course, that's very cool stuff, and infrared is very important. So Spitzer himself had put a lot of effort in lobbying Congress to put satellites, telescopes into orbit, and his first success was the UV telescope in the 60s named Copernicus, and then with successful lobbying in 1977, he convinced them to put the Hubble Space Telescope, which was launched in 1990, 44 years after he originally proposed putting a large telescope in space. So, and as I was mentioning, the reason why Spitzer was the last of the 4 great observatories was that technology needed to be developed, because up until the 60s, in fact, there was no easy electronic way to do infrared detection. And in fact, the first infrared detector was basically essentially a single pixel. And of course, when the astronomers got their hands on it, and this was a group at Caltech, they took it to the Mount Wilson Observatory here near Pasadena, and they put it on a telescope, and they started scanning it across the sky. So you're not taking pictures, we have megapixels, millions of pixels now, but this was one pixel that they would actually they would point across the sky and scan it across the sky, or just let the sky scan across it, and it tells you, oh, there's more light here, less, more, and so on. Oh, there's something very bright there, and that they were looking at the galactic center. Of course, years later, when we have arrays that has lots of pixels that we can do electronically, this is the our galactic center imaged with the Spitzer Space Telescope's detectors. The telescope had sort of 3 different sets of instruments. There was the infrared array camera, which did wavelengths between 3.6 and 8 micron imaging. A micron is basically the center of optical light, that we see it as half a micron, and the longest wavelength that we can see is essentially 0.7 micron. So this is much, much longer wavelength than our eyes can see. There was the multiband imager and photometer for Spitzer, which did 24 to 160 micron imaging. And then there was the infrared spectrograph, which took spectra between 5 and 40 microns. And so we were able to take images. This is an optical image of what's called the Elephant Trunk Nebula. And you can see what we were talking about before, how infrared lets you see through that dust. And so we could now see the stars behind that dust. And so now I'm just going to sort of walk you through, starting in our backyard all the way out, all the sort of great discoveries that Spitzer enabled. One was the ability to measure the sizes of asteroids, because you can never quite get a good sense of the size of an asteroid unless you can physically resolve it. Like in these cases, more often than not, they're just a dot in your telescope. But if you have a sense of what the reflectivity is, that is, more often than not, these objects are not very reflective, but the amount of heat that they're emitting, because they're absorbing sunlight, can give you a good sense of their size when you compare it to their optical emissions. So this way, Spitzer has measured the size of over 100 asteroids. So it's giving us a good census of things that are right in our backyard, which more often than not, we can't get a good size for them. But once you have a good thermal infrared measurement, combine it with the optical, and you can tell whether how big the asteroid is. Of course, then there are comets that come through, and the comet when it has this halo, it's very hard to see the core, but in terms of when you look at it in infrared, you can really see the core as well as the dust and other things that are coming off of it in a much more detailed fashion. And in fact, Spitzer was flying during the what's called the Deep Impact Mission, which was a mission that went and smashed a projectile into the comet nucleus to bring the more pristine material from underneath the surface of the comet to come out, as opposed to the surface of the comet, which as it passes by the sun over and over again, gets chemically changed because it's interacting with the sunlight. But here, what's underneath it is sort of the pristine building block of materials of our solar system. And so when the impactor hit, it was in a position for Spitzer to take a spectrum of it. So we got a very good spectrum of the different kinds of things that would have existed at the beginning of our solar system. And then one of the biggest surprises, and this is a very strange one, is the fact that we discovered the biggest ring of Saturn. And you would think, well, if it's the biggest ring, how did you miss it all this time? Well, the reality is that it's a very tenuous ring, and so it does not, it's not thick enough to scatter a lot of optical light, so that it had gone unnoticed. And in fact, there's a lot of dust coming off of one of the moons that's basically populating this ring. And to give you a sense of scale, that's how big that little dot at the center is, how big Saturn is. You know, this is an artist concept with respect to how big this ring is. But this ring glows in the infrared. It's warm enough to glow at 24 microns, which is the wavelength that Spitzer discovered it at. Going further out is, you know, stars in our galaxy. Stars themselves, of course, form, and our theory of how they form in these dense clouds of gas and dust, and we can't really see what's going on there in the optical. So you have to look at wavelengths that can penetrate this dust and gas, because that dust then, the gas then collapses into a sphere at the center, and that's where you get fusion starting that will become your star. But then around it, a disk forms, and that's the disk from which planets are forming. And so this is one of the cases where, you know, this is a star formation region, and you can penetrate the dust and see the stars forming in these clusters here. Now, this is actually what we're called the pillars of creation. This is the Hubble Space Telescope optical image, and you can see how these pillars of dust are really hard to see through, but you can see through them in the infrared. Here is, again, multiple generations of stars, and you can see what were dubbed the mountains of creation, which is that image that we're looking at just now. And this is sort of two sections near there where you can see the pillars of creation again, where, you know, young stars forming, and in particular, you can see this one star forming at the tip of it, because their nearby stars have formed a pressure wave, and it's compressed that region, and it's formed a new star. And then this actually allows us, when we're looking at young stars, to actually try and study if planets may be forming. So we don't have the resolution to pick out individual planets. But as I was saying, there's this disk that forms around the star. And if a planet starts forming around the star, it's going to clear out a region. So you're going to have a gap in that disk. And again, this is an artist's concept, but and of course, if you have even a larger disk, you can have multiple planets clearing it out. So you can have multiple regions where the planets have formed and are clearing out their neighborhood. This is actually, if you look at it, it might be reminiscent of something more familiar and something that we just talked about, and that's Saturn. And in fact, people didn't consider the fact that the reason Saturn has these very well worn gaps in its rings is because there are moons in there. They're called shepherd moons, which keep the rings in these very tight shapes, but also clear out certain regions. So we had precedent for this. And so we looked at disks around nearby stars. And so what you would expect is, if it's just a star, its spectrum from the shorter wavelength light to the long wavelength light, representing hotter regions to cooler regions, is just this drop. But then if it has a disk, that disk absorbs some of that light and re-emits it in longer wavelengths. And so you get this sort of flatter spectrum than you would get when it's just a star. But if there's a planet that's cleared away, so the hotter region doesn't have that excess added to it, but the further regions do. And on the right, these are actual spectra that we saw, where you see that there's a disk with no gap, but here's a disk with a gap. So even though we don't see a planet necessarily in there, this is pretty good evidence that something needs to have cleared that inner region of the star. And most likely, we guess that it's a planet. And there's a really nearby star with a disk, which is called Fomalhaut. And we're able to see the 450 microns actually is from a telescope from the ground. That's, you're going into what's called a submillimeter. But in Spitzer's image in particular, 70 microns, you see another gap here. This is an edge-on disk that has been cleared out. So this whole thing is about 370 astronomical units across, which is about 5 times our solar system. But we have this sense that, again, there's a solar system forming and clearing out the disk for this star. And of course, we did a lot of spectroscopy, and the cool things are there's a lot of things that are common. Water is very common around across the universe, but these more complex organic molecules are already within those disks of material, which is very encouraging for eventual life to begin. But then when you get to older stars, what happens? And in older stars, which is a little bit more like our sun, is you have these sort of bits and pieces of rocky debris that every once and again collide and create a lot of dust. And that dust is there to absorb the light from its host star. So if we envision this again, this artist's conception, when you have these collisions, you may not be able to see the rocky objects themselves, but once they collide and create dust, this dust stretches out and becomes much larger and has a much larger surface area, and so absorbs and re-emits it in the infrared and lets us see these. These are called debris disks because they're, they're debris of these collisions. And so what we see is certainly there's a lot more of these disks in younger stars, which is stuff that's left over from their formation. But for the later ones, it's certainly fewer, but we still see them. That is, so why is this interesting? Well, you're not going to get debris created when gas giants pass by each other. You're going to get it when rocky planets collide or asteroids collide. So this is good evidence that there are rocky objects out there, even though they're too small for us to detect. We can detect the consequences as once in a while they have collisions, much like in our solar system they have had in the past. So a lot of the stars like our sun, 20 to 60% have dusty disks. Does that mean maybe does rocky planets? Potentially. We found lots of water in clouds around young stellar objects, which potentially hopefully gets caught up into the planets. Our moon formed from a giant collision between planetesimals. But a lot of stars now at that age do not seem to have a lot of dust. Does that mean large moons, are rare? And of course, tides. We know tides are important for the evolution of life, but this is all sort of, we can't image the moons or the creation of these things, but it's interesting to look at the likelihood of these kinds of collisions that will give us a sense of what's going on in these faraway stars that are stars like our sun. So still talking about stars, but in terms of, instead of secondary evidence, what could we find? Could we find planets? Well, Spitzer was not a planet finder, but there are a little bit before the launch of Spitzer, the first exoplanets were found, that is, planets around other stars. And one of the ways they were found was what's called with the transit technique, or with the eclipse technique, where if the planet and the star are properly aligned in our line of sight, then as the planet passes in front of the star, it casts a shadow, and so there's a dip in the brightness of the star. So a large number of planets were found in this way. And again, these are not but then Spitzer would follow them up. This is not the discovery of planets, and these were not Earth-like planets. They're very large and often very planets that were very close to their stars. And remember, this is not imaging of these planets alone. To Spitzer, these were just a dot. But so we observe these planets around, known planets around stars. And oftentimes these were hot Jupiters, that what we call them, because they're Jupiter-like planets, but they're way in closer than the equivalent orbit of Mercury. And it's the combination of the star and planet light together. But these Spitzer made the first direct observations of planets outside our solar system. So it's not, the shadow of the planet, but in fact, these were the light coming off of the planet. So let me play this animation for you to give you a sense, because remember, the planet is warm, which means it's also emitting infrared light. The star is emitting infrared light. So now you have the combined infrared light of the both, but if the line of sight is right, as the planet goes behind the star, you get less light. And as it comes out, you get more light. And so this was a way to measure the temperature of the planet that was orbiting the star. And so these are two of the cases. Again, it's a tiny, tiny fraction, but the engineering on the cameras were so good that we were able to pick up this, fraction of a percent dip. And a couple of the ones that we observed were about 1,000 Kelvin. And we looked at several more of these. And in one case, in fact, the planet wasn't actually even going behind the star, but we were able to follow its general path, because one side is warmer than the other as it's going around the stars. So as it's starting to show the hot side, we start getting more and more increased infrared radiation. And then as it's showing us its night side, we're getting less infrared radiation. So in this way, we could actually follow the planet's orbit. So the animation you're seeing in the background, of course, is an artist's concept. This graph that you're seeing is actual data, and that's what the animation is based on. And so Upsilon Andromeda B, was showing this, significant difference or a fair difference between the night side and the day side of the planet. So we had observed night and day on a planet around another star. Another one, HD 189733b, was actually very interesting as well, because we did the same kind of observation. In this case, it was going behind the planet, but as it, crossed in front of the star, you can see it blocked some of the starlight. The secondary transit, this is when the planet goes behind the star. But notice it's not a straight line. In fact, it actually goes higher as it's showing us more and more of its daylight side. But what's interesting is that this particular planet did not have a huge day-night temperature difference. And since it's a Jupiter-like planet, how do you not get a huge day-night temperature difference? You need high winds or fast winds to redistribute that temperature throughout the planet. And the calculation showed that it would need 6,000 mile per hour winds to redistribute the temperature. And so this really gave us a sense of what kind of atmospheric activity this planet needed to have. So think about this. This is literally a weather report for a planet around another star. Tonight on, your AccuWeather tonight will be, 6,000 mile per hour winds. So this was a great discovery, which was very much unanticipated from the launch, but we were able to do it because we got these large numbers of exoplanet detections. And we also use the same technique to get spectra of planets outside our solar system. And again, we take a spectrum of the entire, it's a dot to Spitzer. So when you're taking the spectrum, you're taking star plus planet spectrum, then you wait for the planet to go behind the star. So you're getting just the star's spectrum. You subtract the two, and what you're left over is with the spectrum from the planet. And so this is an actual, again, spectrum from the dots are the spectrum, and what you're seeing is, various models about what the spectrum of the atmosphere of that planet should be. And we did find water vapor molecules, definitely. So let's go on further even still than our galaxy, our stars in our galaxy. So now we're going to other galaxies nearby. And so this is images of the Whirlpool galaxy. The left is optical light. You can see that it's a lot of stars. The right is infrared. You see the stars are warming all of that dark lanes, which are dust. And so here we're seeing the glowing of the dust. Here's a famous Sombrero galaxy also. Again, the dust, now we see it glowing. Gives us a new sense of sort of the temperatures and the conditions in the dusty regions of these galaxies. The other thing that we were able to do is what Spitzer was able to do large surveys across the sky to find interesting and unusual objects. And so here's the thing about, by the way, this moon is here. We didn't look right next to the moon, but this is to give you a scale. That this is how big a region of sky Spitzer was able to survey. And so, but how do you find anything interesting in this? There's just tons of objects in here. Well, one of the things that happens with galaxies, and this is what I was talking about, the redshifting and of the universe, where as the universe is expanding, the light wavelengths that are emitted get Doppler shifted such that they go to longer wavelengths, is that galaxies have a peak emission around 1 micron. And as the object is redshifted, it actually shifts that peak into the Spitzer waveband so that it's not necessarily that bright in the optical, but it certainly suddenly becomes very bright in the infrared. So here's an image of a piece of sky. You know, there's lots of stars and various objects, and those lines are just saturated pixels. So, but if you look at it at 4.5 microns, suddenly you see this whole chain of bright objects at 4.5 microns. So what this is saying is that it's helping us pick out infrared bright galaxies which are in these clusters. So where's Waldo? Well, you have to stare a little bit, but if you stare in infrared, you can actually start picking out lots of galaxy clusters. And galaxy clusters are sort of the large scale building blocks of the universe. And then we go back in optical, and so make sure that the ones that we think are members of the cluster are in fact members of that cluster. And so this is the change. I mean, initially the red line is basically how many clusters we had. We didn't have them at high redshift, which means large distances, but Spitzer was able to add an enormous number of clusters that were previously unknown using just the technique that I just showed, because as things redshift, their peak emission goes in the infrared and makes them preferentially bright in the infrared. Then sort of what's near and dear to my heart is studying supermassive black holes at the centers of galaxies. Now, sometimes that's easy because if material is accreting onto them, they become very luminous. But sometimes, you know, if it's at the center of a galaxy, it's difficult to see them because there can be lots of things blocking your view and a dust lane along the way. But if you look in the infrared, the bright center of this universe is clear that, you know, there's an active galactic nucleus there, which is this supermassive black hole that's accreting material, and that material heats up as it's falling into the black hole. And so we can pick out a lot of these active galactic nuclei in cases where, for example, in the Hubble Space Telescope image, in the optical, the dust blocks that view, but in the infrared, it becomes very obvious. And similarly, as we're used to, you know, taking X-rays, because X-rays are also penetrating, you can see them. So we were able to, you know, find lots of these hidden supermassive black holes at the centers of galaxies, and then verify that they were in fact these active galactic nuclei by doing these kinds of large surveys. And finally, one of the big things that we did was, again, to combine multiple observatories, where again, the faintness, as something is redshifted, it's going to be fainter, a lot fainter than expected in the optical, and then much brighter in the infrared. And we found these very, very old galaxies, very early in the age of the universe with this technique. But they also seem to be somewhat mature, in fact, in the sense that, you know, based on modeling, what we were seeing is that the amount of light that was coming in infrared indicated that there was a lot of older, sort of standard mature stars. And so Science News picked that up and sort of said that, you know, even though it's the early universe and everything should be a baby, we were getting a lot more mature ones, and they named that one as Herman. So it looks like when galaxies form, some of them form stars very quickly so that they can become mature very quickly. So then once we ran out of our cryogen, that's when Spitzer became the warm mission. And you know, we went from 5 degrees Kelvin to 30 degrees Kelvin. But then only one of our instruments worked, which was the infrared array camera, and only at 2 wavelengths, 3.5 and 4.6 micron, 3.6 and 4.5 microns. But then we were still able now to dedicate it, solely to very specific tasks. So certainly we could, make large scale images as well in those two wavelengths. But then because now we weren't switching between one instrument and the next, we could observe and stare for long periods around large regions of sky. This is the Orion Complex. It is forming young stars, and one of the hallmarks of young stars is they spin very quickly, so you can actually pick them out based on their variability. And this was allowed because we were, staring at it for 40 straight days. And then we were able to do exoplanet follow-up in a way which we hadn't been able to do before. This was an object called TRAPPIST-1. It was a Belgian astronomical-led team that, from using a ground-based telescope, found this very odd transit in front of one of the stars it was monitoring. And as you can see, there are multiple dips, and the idea was that there should be multiple planets, but it was very difficult to figure out which planets were which, because every 12 hours you have daylight, so you would lose the cadence, you would lose the pattern over 12 hours. But then Spitzer initially was granted 500 hours of observations. And so this is an artist's concept of what that was like for this TRAPPIST-1 system. And instead of the 3 or 4 planets that they thought orbited TRAPPIST-1, in fact, there were 7 planets. Now, this is a star that's much smaller than our sun, hence it's a lot redder. And at the bottom, what you will see is the actual data matched to the animation to give you a sense of how, as the planets were passing in front of the star, we would get these dips. We're not getting the secondary dips because the planets themselves are not that warm, so that, as they're going behind, there isn't as big of a dip and as a noticeable dip when they go behind. If the star was warmer, the planets would be warmer, and so their contribution when they went behind the star would be larger. So this is the TRAPPIST-1 system. It's actually, if you compared it to our solar system, it would fit entirely within the orbit of Mercury. The star itself, again, is much smaller than the sun, but there are 7 planets in there. And we've learned a lot about those 7 planets. In fact, one of the key things that we're always looking for is the habitable zone, that is where liquid water can exist. If you're too close to your star, you're going to be too hot and too dry. If you're too far from your star, you're going to be too cold and icy. But there's definitely 2 planets that are well within the habitable zone of that star. Doesn't mean there's liquid water, but the conditions are right to actually have liquid water on those planets, and potentially maybe on another one on the dark side, it would be just cool enough to have liquid water. And after about 1,000 hours of observations, we were able to actually get densities because we could measure the masses because of what's called a transit timing effect. That is, their orbits start affecting each other. And how massive they are affects, just slightly earlier or later arrival times in their transits. And this is a very interesting system because they're all just about or below the density of the Earth. There's a few that are lower, but it's really an interesting sort of set of systems. It's an interesting system. So, and again, we have these, definitely a couple, maybe 3 of them in the habitable zone of TRAPPIST-1. So we got from the very nearest, that's one of our nearest stars, and then we've gotten even more objects now where we're, again, finding out these very early, very young galaxies that we've been detecting with Spitzer during the Spitzer 1 mission, so that we can see that galaxies are forming very early on, right after the Big Bang. And of course, over the years, we've certainly made a lot of pretty pictures, and now we've been on the covers of various astronomy texts. We've wound up in various movies. That's a large Spitzer image of a star-forming region. But the critical part is that we've been trying to answer the big questions that NASA has put forth. Where do we come from? Are we alone? Where are we going? And all of these questions have had a great contribution from Spitzer in this over 16-year mission. And it was the work of many, many people collaborating, and multiple astronomers, hundreds of astronomers across the planet using Spitzer by proposing different ideas. And there are always ideas that were novel and interesting. And so that's where I've tried to concentrate some of the results, but there are many, many results that I couldn't get to, but it is a great success, and the archive is still there, and there's a lot of discoveries yet to be made. So thank you very much, and I'll take questions now.
So don't be shy, go ahead.
Yeah, Trace One, the transiting system, the system with a transiting exoplanet, one of the first discovered, was at first rumored to have evidence of a ring around it in the transit, in the shape of the transit. Did this pan out?
Not that I'm aware of. And I think that's actually something that actually, I don't have an image of it. So is a really good target for the James Webb Space Telescope, because it has, it can really do a good follow-up on that, particularly on a lot of the exoplanets. But because now it's in the infrared, it can really look at, it has a much larger aperture as well. So it can certainly help to sort of put that to rest once and for all, either true or not.
Somebody has a question in the chat.
Chat up.
It just says thank you.
Oh, well, you're very welcome. But yeah, any other questions?
So we'll let our students wait a while to get up their courage to ask. So definitely please ask. But I had a question. So all the planets in the TRAPPIST system, they're very close to their stars, so there's a good chance that they're going to be tidally locked. And the one planet that was kind of in the middle of the habitable zone had sort of like a bare spot which looked like water, and then ice around it, which I think is called an eyeball planet, right?
Yes, sort of. That's again a sort of, these are again artist concept based on what we would expect from them, in the sense that this one is potentially too hot on the stellar side. But if it is tidally locked, if it has ice on the other side, then over time that may be, on the terminator, in fact, it may be too cold on this side, too warm on this side, because it's not, it always has one side towards its star. But then in that transition region at the terminator, you may actually have water, because it's dusk there all the time. But you're right, that is the reason why that has been designed as that, is that more likely than not, these planets are likely tidally locked to their star.
So,
yeah, keep in mind that Mercury and Venus are tidally locked to each other. For every 3 orbits of Mercury, there are 2 of Venus. So for something like the TRAPPIST-1 system, we might expect these tidal effects to be much stronger.
And in fact, I mean, that's the thing. That's the reason we've been able to get the masses for these planets, is because they are tidally interacting as they pass each other's by. And so how much they slow each other and speed each other up over the 1,000 hours that we've looked at them is what's allowed us to actually get not only the sizes of the planets, which you get because we know this is it's an M star, so we know the size of this particular kind of M star. So the dips tell you the physical size of the planet, but the tidal interactions, because we've been able to look at them for so long, and with Spitzer, has given us their masses. So now that's why we can actually get a density for them. And in fact, because of that, TRAPPIST-1 right now is the only other this basically is the best studied solar system outside of our own. We don't have this kind of information on most of the, and any of the certainly not to this precision on any of the other sources that we've seen. We've had a few systems that have had transit timing variations with this tidal interactions, but not with 7 planets.
How far away is the TRAPPIST system?
It's about 40 light years. So not human lifetime close, but certainly it's one of a very close family of stars. And in fact, because this is a very dim star, if it was much further, they could not have done it. They could not have detected the planets around it with a telescope from the ground. It's a relatively small telescope.
Okay, so questions from the students? Dr. Gorjian also said if you were interested in talking about JPL, Caltech, internships, careers, he'd be willing to answer those kind of questions. Okay, well, all right. So if no one has any more questions, let's just thank Dr. Gorjian again for a fantastic talk. And yeah, have a great Friday, and see you guys next week. Bye.
Thank you so much.
Oh, you're welcome. Happy to do it.
Fascinating.
That was a great talk, actually. So
Yeah.
one of my colleagues was watching, and he was remarking on the amazing animations.
Yeah.
We lucked out, and because my colleague, many of these, not all of them, were done by Robert Hurt, who he and I were actually graduate students together at UCLA, and he was trained as an astronomer and went to work at the Infrared Processing and Analysis Center at Caltech, which was the home where NASA put the Spitzer Science Center. And when he transitioned to the Spitzer Science Center, I mean, he'd always liked working on graphics and things on his own. It was his hobby. And the project that he was working on before this, which was a 2-micron all-sky survey, he was doing a lot of the graphics for that. So they actually created a position for him to do graphics and animation, because he certainly understood the science of it, and then was able to, produce these kinds of animations. And then, but it was actually a lot of work. And so another person was brought on, and we're in LA. So it was this particular animator had worked on SpongeBob and various other things. And so his name is Tim Pyle, but Tim had not, was not an astronomer, but Robert was there. So and I've been also one of the people, the astronomers, we would talk and describe it to him. He's a very smart guy. And he was able to create these animations, similar animations as well. So that has been the consequence of several things, in that, partly just Robert Hurt's innate interest in art, and also the fact that we are in a place where, animators are prevalent. And so we were able to take advantage of that, and we've tried to make as good a use of it as possible, because in trying to communicate with this, and it's not just for, the lay public, it's really useful for astronomers as well. So that's been our lucky break here, as well as just hard work on the parts of Tim and Robert.
Yeah.
And some of your funding came from NASA, and NASA usually has a requirement for public outreach, right? Or they have some part of the grant that's geared to that, or no?
So that was the case. So during the the Spitzer Science Center, the Spitzer mission is all NASA funded. So part of that, at the time, NASA had a requirement for, I think 1% of the budget of any mission to go to public outreach. And so that's what we were using for it. And in fact, we, part of that was, various different outreach events. But the other part of it is we started using, which is another program that I'm a part of, to do outreach to teachers, to high school science teachers. Because one of the things that we hadn't, other people had recognized, and we continued, was that what we noticed was it's a very odd situation that people who become, junior high and high school science teachers never actually do science before they get there. They're trained in the knowledge of science, but not in
Right.
the doing of science. And so what we ended up doing is we would start recruit every year a small group of high school science teachers who would do a research project with one of the astronomers, me being one of those. So that, and then we would take them to a science meeting, the American Astronomical Society meeting. Most of them have never been to a science meeting, which is, ridiculous. It's like, if you're a basketball coach, you've never been to a tournament, or you've never played basketball. You only are there to teach basketball. No one would think that's a good idea, but and this is not a criticism of the science teachers. This is a
No.
criticism of the process of how we've come to train our science teachers. So we take them to a science conference, we do a research, we get them the data, we provide them tools that are similar to the tools that we would use, and then they present it in a science session in a following science conference. So that they're the ones who are doing the presenting, they're the ones who are defending what they've done. It's at a poster session. So but that grew out of this requirement of spending money on outreach, and then that finished. And so we basically have been trying to get funding from different sources to continue that, and we are still continuing. That's called the NITAR program, the NASA IPAC Teacher Archive Research Program. But yeah, now NASA has shifted away from that, in that they have now created a separate pot for outreach called it's called the Science Activation. And so different groups, including Spitzer Science Center, which is at this center at IPAC at Caltech, as well as others, have joined up so that we can do the outreach. So NASA is still funding outreach, but not as a part of the mission, because it often tended to reproduce each other. So Hubble was reproducing what Spitzer was doing, which is reproducing what Chandra is doing. So we wanted to be a little bit more efficient with the funding. And so it still does that, but it's not as a part of the mission.
Smart.
Well, actually, Varoujan, so actually I'm looking in the chat. There is now a question. Hold on a second. So actually there's two questions now. So Sergio Laporta said, thank you very much. But he also said, have they thought about starting that as a field of education so that someone could minor in it? And
yeah, sorry. So that intersection of the art and the astronomy, to train people specifically to do that.
Unfortunately, not because the opportunities are very scarce in that sense. That is, in terms of the sheer number of observatories that are available that would make use of this would be too few. But it is not a. I think it's one of those things. If there's a general area, which I think they're starting to do, and there may be a couple of areas where general science communication. There has been science communication as far as writing, for example, science journalism and so on has existed as a college major, but I think this may be a broader area where you have science communication, where you bring not only sort of the journalism side of it, but sort of the video production and the animations and the art and so on. And so that may be a place where that can actually be very useful, because having just lived through this past year of course, communicating what COVID was, communicating what, how it affects people and so on and so forth. I think it's been done at various levels of competence. And I think that's partly because there's no good training as to what's a good way to communicate. I mean, there's a lot of studies that have been done, but there's no sort of cohesive training that people go through as to what's the better way. We've done a lot of trial and error and have come up with something. There are education research that has come up with it. There's sort of other research done by NASA and NSF. How do you communicate all of this stuff? But previously it was almost always about the text or the audience, but never bringing in full on the artistic side of the when you draw something, what's the important thing? How do you draw it to communicate whatever you want to communicate? If you're making a video, what is it that you want to communicate, and what should you do, what shouldn't you do? So there's a lot of things that I think that has the potential to do that. But I think if it's just astronomy, it's not likely. It would overwhelm the number of jobs available. I'm not saying that it should be just for jobs, but it would be just the rate of absorption of people like this is very low.
Right.
Okay, so actually, now there's another question from our SPS president, Soban, and he said, I have questions, but it is not related to the talk, mostly about JPL. Dr. Gorjian, do you have any information about JPL tours for students and internships for the summer?
So unfortunately, in terms of the tours, there's two ways of getting, there was two ways of getting tours of JPL. One was there was an official website where you could sign up, where they gave group tours. That would, oftentimes would fill up, it almost always filled up very quickly, but so you sort of had to do it like you're signing up for the vaccine, you sort of get up at the morning of when the dates would be released and you'd sign up for them. Unfortunately, most of us are not physically at JPL at this time. It's a need to be on lab requirement. So if you're building something on a mission, you're allowed to be on lab. Everybody else is not on lab, and we don't know when we'll be going back. And even then, we don't know when these public tours would start up. Now, if you know somebody, then that person can sign up to give a tour of up to 10 people, or up to 9 people actually. But again, that I'm not sure when they're going to be allowing us to give personal tours. As far as the summer internships, if you go to education.jpl.nasa.gov, it has a listing of the internships that are available. There are year-long internships, there's summer internships. At least, unfortunately for this summer, it's actually a little bit late since most people, I think, have been signed up already, but you can certainly go and check and contact the education office at JPL to see it. But again, one of the cool things about doing a JPL internship is to physically be at JPL, but all of our internships this summer are remote, as were our internships last summer. So there's still a good advantage of working with people at JPL, getting a sense of what's being done there and who works there, but it's not quite the same as physically being there.
So you mentioned there's a Spitzer building, right? It's like, I think I've seen it. Or is there a Spitzer building on the Caltech campus, or?
Yes, and that's sort of, it's wrapping up now since the mission is over. So the way NASA missions work is they put what's called the Science Center at a university campus. And in 1984, the first infrared space observatory, which was called the Infrared Astronomical Satellite, IRAS, was a collaboration between the United Kingdom, the Netherlands, and NASA through JPL. And so the Science Center for that mission was placed on the Caltech campus. It was called the IRAS Processing and Analysis Center. Then it became the hub of infrared missions for NASA. So the Spitzer Science Center was also placed at IPAC. And we've had various other, mostly but not uniquely infrared related tasks that happen for NASA are based at IPAC. The Space Telescope Science Institute, which was set up for the Hubble Space Telescope, is on the Johns Hopkins campus. And now the James Webb Space Telescope, which is actually primarily the successor to Spitzer, not really Hubble, but that's also on the, part of the Space Telescope Science Institute on the Johns Hopkins campus. So there is a building there. In fact, it was the administration building, and it's, maybe says something about Caltech, where they would give up 3 floors of an administration building to a science mission. But that's what happened, is that we took over because we became the largest part of IPAC at that point. But now that the mission is finished, we're wrapping up. So we're giving up that space back. And in fact, they're taking up parts of it for new missions that are being based at IPAC. But if you go to Caltech, still one of the buildings, corner of California and Wilson, is it will say the Spitzer Science Center.
No, because I was at Pacific Coast Gravity meeting like 5-10 years ago, and it's like an angular building with red bricks, like reddish color. Is that?
That's the astronomy building. That's not where the Spitzer Science Center is. So that's the astronomy department is there.
Okay.
And the building right next to it, which is a sort of a 70s, brutalist architecture kind of thing is it was where the Spitzer Science Center is.
Okay, all right. So, you'd mentioned that they actually took some administration building and reconverted it for science. It's kind of
Yep.
what happens on this campus.
Yeah, no, it's called well, yeah, I mean, I did my undergrad there. That's, you know, the administration building and various, you know, it had 3 floors. They actually added a conference floor on the roof. But yeah, it's when the time came, they actually vacated several two of the floors, as well as, you know, adding the 3rd floor on top with the conference rooms for the Spitzer Science Center. So that is definitely showing you what the bent of the university is there. But then again, once we started getting smaller as the mission started going from the cryogenic phase to the warm phase, and now that we're basically mostly doing the wrap up, one of the floors was given back to, you know, for various administrative purposes, and then eventually, but I think we're going to keep the last floor because we've actually gotten a new mission that's a much smaller mission, but an infrared mission that will be run from and staffed by people on the 3rd floor. So, but then that's all under the umbrella of IPAC, which now is no longer the IRAS Processing and Analysis Center. It's not even the Infrared Processing and Analysis Center. It is now just IPAC, like KFC, because KFC is no longer Kentucky Fried Chicken, apparently.
Just, if you might, a completely different question, but I was just wondering if you could reflect upon your time at Caltech, and what would you say were the positives of going there, and if there were any negatives, what those would have been?
So I am very ambivalent about having gone to Caltech as an undergraduate. Okay. So I think that's by which I mean there are about as many positives as there are negatives. But again, that experience is now 30 some years ago. I do know there have been improvements, but I feel, talking to some of the more current undergraduates, not enough. They've certainly made great strides in diversity. There are more women now than when I went. There's you know, they're expanding. They're trying to do more minority enrollments. But the difficulty, I think, with Caltech is teaching is simply not a priority, and it wasn't then, and it doesn't seem like it is now. And this is not a rip on the professors themselves. The structure of the university just doesn't really promote that. That is, it's you as a professor, you're rewarded for your research and bringing in grants and graduating graduate students, and you know, and all those kinds of things. Being a good teacher has absolutely no effect, or being a bad teacher has absolutely no effect on your status as a professor. And there are some who feel in their bones that it's important to be good teachers, and they are. There are some who feel that it's important, but they just don't have the training or capability to do it. And there are some who think it's just a nuisance. But there's no difference between them in terms of actual, you know, how the university is run and your promotions or salaries and this and that and the other. So I think that's a critical issue, I think, that Caltech faces. And in having such a restrictive admissions, that is, you know, a very small percentage of the students who apply get into Caltech with the sort of label of best and the brightest. And I think what my impression was that, well, you're the best and the brightest, go figure it out yourself, which is, there's some validity to that approach, but that's not the same as being a good teacher. That is, good teaching isn't you go and figure it out yourself. A good teacher is, I figured out, you know, these are the critical points that you must take away, and I will, you know, put it out there. It's not, you know, chewing the stuff for them to swallow it. Anytime I say being a good teacher, everybody somehow thinks it's to make it, you know, easier for the students. The best teachers I've ever had at various levels throughout my entire, you know, educational career were the hardest classes that I ever had. But in each of those classes, as hard as they were, I felt that my hard work was being rewarded with greater knowledge and understanding for me. In many cases, when I was an undergraduate, the hard work, and it was incredibly hard work and many, sleepless nights and so on, oftentimes just felt like I was, swimming upstream and I was not getting anywhere. And that was not just me, many other students. And that's the part of the things that I sort of get reflected back from undergrads that I've talked to more recently. That I think undermines so many different aspects of having good students. And just as a piece of evidence, what I would say is their approach then, and I suspect unfortunately now, is a mining operation. That is, you're looking for the diamond in the rough, the one thing that one student that'll be the great one to solve all the problems from that. And every class has a few of those. So they're not really concerned about the other students. And in fact, my class had two of them who were incredible. I mean, every distribution, whatever tests we took, there was everybody. And then there were these two other guys who were just like way ahead of us, just incredible. And I think in many ways, a lot of the professors there felt that that was their job, to sort of highlight and bring out these exceptional people. But that approach, these two guys who were like the best two physics students in our class, both left the field for graduate school. They were so disgusted by that, even though they were the best, even though they're literally what everybody there was looking for.
Wow.
But they left. One went and got his PhD in electrical engineering. The other one got his PhD in medical imaging. So don't listen to the guy who was in the middle of the distribution. But if you're going to listen to the guys who were supposedly at the top, they just didn't like it. This whole idea of we're just going to make things, leave it up to you, or make it difficult enough so that the cream rises to the top and everybody else, well, you weren't meant to be a physicist anyway, so never mind. As opposed to training people, as opposed to saying, okay, what is it? And what's interesting is the astronomy department was different than the physics department. I was in the astronomy department, but I had to take a lot of physics. But the astronomers tended to be a lot more like, oh, you want to be an astronomer? This is how you be an astronomer. Do that. No, you did that wrong. Do it again. And much more of an apprenticeship kind of thing. And the research, but here's the good part of it. So the ability to do research at Caltech was great. You got to do research very early with incredible people early on. And that, I think, really fired us up all a lot. And that was really exciting to be a part of. And you are in this very select group. I have friends who were undergraduate friends that I worked with all those sleepless nights way back when. We've all kept in touch, became very close friends at Caltech, and have kept in touch since. So that camaraderie, that small group, and the smallness of Caltech has its advantage. But then again, it's a small campus. It used to be 200 undergrads per class, which is what I was in. Then they upped it to 250. So it's a total of about 1,000 undergrads. There's more graduate students than undergraduates. And as a big school, big schools tend to provide you more opportunities. You can take an architecture class. You can take an art history class. You can, I mean, not that there weren't some of, there's a humanities department there as well, but it's a much more limited one. You don't have the choices that you may have, when you go to a bigger school, even a bigger engineering oriented or a science oriented school. But Caltech is so small that even when I was there, biology was not a big thing at the time. So if you wanted to take an intro biology course, it really didn't exist. And now, of course, a big part of Caltech, was part of the genome project, and biology is big, and so on and so forth. But now they've changed things around. But that's a constant. But again, that's a consequence of the school growing. But it's still not at the size scale of any of this, Cal States or the UCs, where, to me, as an undergraduate, you want it to be an expansive experience. You certainly want to really delve into your field, but at the same time, you want to be able to interact with different people, more people, different topics, different things that are outside of your major, all of which I think, both, are interesting as a human being, but also, even a larger electrical engineering department or larger, various other departments. There's a few very large departments at Caltech, but some of the other departments aren't that big. They're very specialized. So you don't have the breadth of that field, even if it's a science or engineering field, but much less so of things that are outside of science and engineering. So lots of different things to sort of put in there. Sorry.
No, thank you.
Okay, yeah. So I'm like I said, it's 6 of one, half a dozen of the other. It's been and I think everybody has to sort of A, be informed, but B, it's a very it's just an unusual place. There aren't many places like it. There's certainly distinct advantages, but there's definitely some distinct disadvantages.
Oh, thank you. Thank you. That was very informative.
Yeah, actually, very nice here. So actually, I have one last question, and and that's we recorded this. Now, do you want a copy? And actually, normally what we do with our recordings is we put them up on our colloquium website for those people who couldn't come. But however, like in your case, you may have some like paperwork with NASA to go through. Anyway, so we'll send you the recording to you. And if you give us the okay, we're going to put it up for people to see that didn't come. This was a great talk, by the way.
Sure. Oh, I'm glad you enjoyed it.
But so then, anyway, if you already know ahead of time that, yeah, go ahead and put it up, great. Or if you already know ahead of time, yeah, you can't put it up because of proprietary stuff, then we won't.
There, as you saw, this is cleared, so it should be fine for it to go up. I don't see any problems with that. It should be okay.
I'm sorry, could I ask one more question? And this
Yeah,
is, I'm gonna say this is completely off topic, and this is because I am the professor of Armenian studies here.
Oh,
but if this, I don't, so I was just wondering how your being Armenian had played into anything in your career, if at all, and whether you were able to go to Armenia, to the observatory there on Mount Ararat. And
yeah, so this is actually a interesting story in the sense that I'm an Armenian who was born in Iran. So growing up there, I mean, as a young child, partly because I can't tell you whether I loved space first, and that's because I loved science fiction, or I loved science fiction and then I loved space. But I wanted to be an astronaut. And everybody, of course, used to tell me, it's like, Iran doesn't have a space program. I'm like, yeah, I know. I'm a kid, I'm not dumb. But then unfortunately, the revolution happened. And so we already had relatives living in Los Angeles, so we moved here. So suddenly that reality was much more likely. And then I found out that to become an astronomer or to become an astronaut, one of the ways was to become what's called a mission specialist. So you become specialized in a science or an engineering field. And so I said science of space, and I chose astronomy. Now, historically, there was a very famous Armenian astronomer who established Varoujan Observatory on Ararat, Victor Hambartsumyan. So that's the one name that would keep floating up. And in terms of, at least I could say, well, you've heard of Victor Hambartsumyan, that he does astronomy, but of course I want to be an astronaut, but still. But what was interesting, particularly coming from, Iran and sort of that aspect of the Middle East, is whenever I would say I want to become a scientist, people would, the first question, and this is speaking to other Armenians, relatives, friends of the family, and whatever, the first question was, how are you going to make money at that? So I think in that sense, that would have discouraged me, I think, had my parents not been like, no, fine, if this is what you want to do, go ahead and do it. So they were always very supportive. But in terms of the community, and I understand it, it's a very, survivalist culture. What are you going to do? How are you going to survive? How, and people know, if you're doing something, they understand, even if it's particularly engineering, that's something that you can be productive in, make money. This was so outside of everybody's experience. So I don't blame them in the sense of sort of challenging me on thinking that, it's a little bit like, if any Armenian unfortunately still says, I want to become an artist, everybody just sort of poo-poos it. Now, if they become a famous artist, that's great. But until then, so there's always this, there was that questioning. And, but then also that, I knew of Victor Humbert-Simeon, so there was somebody there, although I didn't know much about him. Now, my grandfather ran away from the Bolsheviks when the Soviets took over Armenia, so I have relatives in Armenia. And so I was able, both as a student, to visit, because of a student sort of, get the diasporan kids to visit the homeland during the Soviet era. And I was one of the first in my family to meet relatives that we had not seen, although my mom had continued correspondence with them and had even a few phone calls here and there over the decades, from the time that my grandfather came to Iran to escape them, the Soviet rule. But I was one of the first to meet relatives there. They didn't have any connections with the observatory then, but then when I went back in 2006, there was, we decided to take my parents to meet our relatives there. And so while I was there, I'm like, I might as well just get in touch with the astronomers there, see if I can visit the observatory. I'd heard so much about it. And then, and they were very welcoming. The director invited me to give a talk while I was there. And so we got to go to the observatory. So I was set up to give a talk. And then just as I was about to give the talk, my dad came up and said, there are people in the audience with an English to Armenian dictionary. Can you just give your talk in Armenian? And I'm like, I know conversational Armenian. I don't know any of the technical terms to use in giving a technical talk. And then it just dawned on me. I'm like, wait a minute, they read this in Russian and they know they probably know all the technical terms. If I use the English technical term, I'll just use Armenian in between and I'll just drop the technical term. And I would presume that they would know it, and it worked fine. And in fact, I was able to do it, or give my talk in Armenian and then use these various, terms here and there. But the Q&A even turned out to be even more weird because they would ask me their question in Armenian, and they had the Armenian terminology for these technical terms, and they would use it. And it took me like a couple of beats to understand that what they said. For example, there's something called cooling lines. Cooling lines are, it's emission from a gas that emits at very particular emission lines. This is basically how a neon lamp works. It's that very colored neon. There's a very specific wavelength of light that's being emitted, and it takes energy away from the gas, and it cools, and by taking energy away, it cools the gas. And in English, we call them cooling lines. But the person who used it asked me about Saratsno Gits, which to me, and I bet to you, all you heard about was Sar and Gits. But that's exactly what a cooling line is in English. I have now associated it with this concept, with this physical concept of taking energy away from a gas and cooling it. But there were a couple of times where that happened, where they were saying something and I'm interpreting it as a common Armenian interpretation. Well, even though the English one is exactly the same words, I have now associated it with a jargon for the field.
Yeah, they calc the English, and it created a completely different semantic field in your head.
Yeah. So and then there was a fairly famous astronomer who was still there, Edward Khachikyan, and he'd done a lot of work in these active galactic nuclei with supermassive black holes at the centers of galaxies. And that's where I was working on. He came up and started talking to me, and he would actually come for visits various times in the US, and we kept up correspondence, and he would come out here and we'd hang out, and we actually worked on some research together. So I actually was able to set up a connection there. And then he invited me, and because of him, I was inducted into the Armenian National Science Foundation. And so I've kept some connections up with Varoujan over the years. But it's unfortunately, and understandably, in a country that's struggling for any kind of financing, astronomy is not a high priority. In fact, it was Victor Humbert-Simeon who, in a very clever ploy of working the Soviet system, managed to get all of that money to build the observatory in Armenia and bring in the money to train the people and have the equipment and so on. But they're doing their best that they can, but it's very difficult. And I wish, I was in a better position to help them, but unfortunately, I'm not in a very good position. I mean, they do various fundraising, and I've tried to help them on that, but it's a difficult time for them, and it's a difficult time for them to not only train students but to hold the students. And in fact, their top researchers have all left to go to other countries because they were actually very good. And so there are some in Germany and some in other countries have come to the US and so on. And that's over, right past after the Soviet era. But then there's not been this really great, they've not been able to really get things going and working as much. But the people who are working there are doing their best that they can.
Thank you.
Okay, so if there are no more questions, and also, like, I should get out of here because I'm supposed to meet some of my students. I have a tradition, after we publish a paper, I take them out for a beer. And so I was supposed to meet them at 4:30.
Oops, sorry.
No. This is, I mean, actually, I like the Armenian discussion, and so we're too. But anyway, Varoujan, thank you very, very much. Nora, this was a fantastic talk. And Sergio, thanks for coming by and participating. I mean, that was a great last question.
Thank you. No, and thank you so much, Varoujan.
All right, guys. Bye. Thanks for the great talk again, and I'll send you the recording. And have a great weekend.
Okay, great. Thanks so much. So long, everybody.
Bye-bye.
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 Bye.